Hello, everyone. Liveliness and excitement usually go hand in hand with crowding and noise. Freedom and spaciousness, on the other hand, often come with loneliness and emptiness. It is very difficult to balance between these two aspects. Just like in quantum mechanics, you cannot determine both the position and the velocity of a particle at the same exact moment. But you can measure each value separately, one after the other. Do you prefer excitement and liveliness, or do you prefer freedom and quiet? These preferences may change with age and life experience. When young, most people dream of owning a house in the middle of a busy city. But with time, that dream often changes. Later in life, people may prefer a peaceful, open place, perhaps a small garden. Why? Simply to plant a few flowers. It may not bring much material value, but it shows a major shift in mindset and expectations as we grow older. It is very difficult to fully explain such things because everyone thinks differently. More importantly, this is a matter of personal perception, not something that can be observed directly. Most of these are subjective guesses, not precise statistical values. The philosopher Aristotle once argued that nature abhors a vacuum, meaning nature will do everything possible to prevent a vacuum from forming. This viewpoint caused major debates in the history of physics. A big question remained: what is a vacuum? In contrast, Democritus believed that a vacuum is the empty space between atoms. In ancient times, scientific and technical knowledge was extremely limited, but these philosophical ideas showed remarkable foresight. According to Aristotle, motion requires a material medium. A fish must have water to swim. A bird must have air to fly. A very simple example is a straw. If you suck the air out of the straw, air immediately fills the gap. If you put one end of the straw into water, the water will rise to replace the air. Aristotle believed this proved that nature hates empty space. Because of his sharp arguments and easy-to-understand examples, Aristotle's viewpoint was considered correct and lasted for more than 2,000 years. Meanwhile, Democritus said that the universe is made of two basic components: atoms and the vacuum. The vacuum is the space where atoms move, collide, and combine, producing all natural phenomena. According to him, these phenomena did not come from gods or mystical forces, but from the motion of atoms in the void. This idea is astonishingly close to modern physics. Actual matter takes up less than 1% of space, while over 99% is empty. However, since there was no way to test it at that time, Democritus's ideas were ignored, while Aristotle's example of the straw was accepted. In reality, the straw experiment only demonstrated air pressure, not the true essence of vacuum. For thousands of years, the debate continued. Aristotle's influence was far greater, so his idea that nature abhors a vacuum dominated, while Democritus's views were often dismissed as heresy. It was not until the 17th century that things began to change. In 1643, Evangelista Torricelli, a student of Galileo, carried out an experiment that created a vacuum using mercury. He filled a glass tube about 1 meter long with mercury, sealed one end, and inverted it into a basin of mercury. When he removed his finger, the mercury level in the tube dropped and stopped at 76 centimeters. Torricelli argued that the empty space at the top of the tube was a vacuum, a region containing no matter, not even air. The height of 76 centimeters was not random, but caused by atmospheric pressure. This experiment proved that a vacuum can be artificially created, directly contradicting Aristotle's idea. However, many scientists at the time still believed the empty space was not truly empty. They claimed it must contain some invisible substance called ether. In 1648, Blaise Pascal, a French mathematician and physicist, repeated Torricelli's experiment to test the role of atmospheric pressure. He performed the experiment at two different altitudes, one at the base of a mountain and one at the summit, 1465 meters higher. The result was clear. At the base, the mercury column stopped at 76 centimeters. At the summit, it dropped to 68 centimeters. This proved that atmospheric pressure decreases with altitude, and that vacuum can not only exist, but can be controlled by manipulating pressure. From then on, Aristotle's idea that nature abhors a vacuum began to be rejected. In 1654, Otto von Guericke, a German scientist and engineer, demonstrated the tremendous power of vacuum and atmospheric pressure through the famous Magdeburg hemispheres experiment. He created two hollow metal hemispheres, about 50 centimeters in diameter, joined them together, and pumped the air out from inside. As a result, even with 16 horses, 8 pulling on each side, the hemispheres could not be separated. When the valve was opened and outside air rushed in, the hemispheres immediately came apart. This experiment astonished scientists at the time, proving just how strong atmospheric pressure really is. During the same period, experiments with vacuum became increasingly common. In 1660, Robert Boyle, an English scientist, designed an experiment to study how sound travels in a vacuum. He placed a bell inside a sealed glass jar and gradually pumped out the air. At first, the sound was still audible, then it grew weaker, and eventually almost disappeared. The result? Sound cannot travel in a vacuum. It can only propagate through matter. Thus, after more than 2,000 years, Aristotle's idea that nature abhors a vacuum was finally disproven. Vacuum is part of the world and the universe. It exists, it can be created, and it can be maintained. Today, vacuum technology is used in many areas of life: incandescent light bulbs, vacuum cleaners, thermos flasks, food packaging, and more. However, debates did not end there. Aristotle still stood as a towering figure of knowledge, influencing science and philosophy for millennia. He had suggested that sound was the motion of air, though he could not fully explain it. In 1638, Galileo Galilei argued that sound was generated by mechanical vibrations. Later, Isaac Newton reinforced this idea, stating that sound originated from the vibrations of matter and propagated as waves through a medium. Newton also introduced the first formula for calculating the velocity of sound. However, Newton's calculation gave the speed of sound in air as only 298 meters per second, which was incorrect. The error came from assuming that sound propagation was an isothermal process, meaning the temperature of the medium remained constant as the wave traveled. In the 19th century, Pierre-Simon Laplace corrected this mistake by treating the process as adiabatic. When matter is compressed and expanded quickly by mechanical vibrations, its temperature changes locally. These changes, though small and rapid, significantly affect the speed of sound. By including the heat capacity ratio in the formula, Laplace obtained a result of about 343 meters per second, which matches modern measurements. This showed that the propagation of sound is far more complex than it seems, depending not only on density and elasticity, but also on temperature and pressure. Returning to the earlier question, if sound requires matter to propagate, then how can light travel through the vacuum of space? To answer this, scientists propose the existence of a special medium called ether. Ether. According to Aristotle, ether was the fifth element, in addition to earth, water, fire, and air. Ether did not exist on Earth, but filled the cosmos, an eternal, invisible medium, impossible to detect directly. In the 17th century, René Descartes redefined ether as an invisible, massless substance permeating all space, preventing the existence of true empty vacuum. He believed that light traveled through space as swirling motions of ether, similar to how sound traveled through air. In 1690, Christian Huygens developed the wave theory of light, proposing that light propagated through a luminous ether. At the beginning of the 19th century, Thomas Young, with his famous double-slit experiment, reinforced the wave nature of light and revealed phenomena such as interference and diffraction. To explain how light could travel through cosmic vacuum, Young still relied on the concept of luminous ether. By the late 19th century, James Clerk Maxwell formulated the electromagnetic theory, identifying light as electromagnetic waves. Yet even he believed ether was necessary as the medium through which these waves propagated. The influence of Aristotle and the concept of ether was still extremely strong. Nearly all scientists at the time believed in its existence. The turning point came in 1887, when Albert A. Michelson and Edward W. Morley carried out their historic experiment to test the existence of ether. According to physical logic, if ether truly existed, then as the Earth moved around the Sun at a velocity of about 30 kilometers per second, it would create what was called an ether wind. Similar to how a moving car experiences air blowing against it, this ether wind should have affected the measured speed of light on Earth. If ether existed, the speed of light should have increased when the observer moved toward the source and decreased when moving away. Michelson and Morley built an extremely sensitive interferometer, using mirrors set at right angles to split and recombine beams of light. If the speed of light varied, even slightly, the interference fringes would shift, detectable with incredible precision, down to fractions of a nanosecond. They repeated the experiment many times, at different times of the day and different seasons of the year. The shocking result: no change at all. The interference fringes remained perfectly still. This meant there was no ether wind, and that the speed of light was constant in all cases, regardless of Earth's motion. This unexpected outcome led even Michelson and Morley themselves to doubt the experiment, thinking perhaps it was flawed or their equipment insufficiently sensitive. But nearly 20 years later, in 1905, Albert Einstein published his special theory of relativity, redefining the concepts of space and time and removing the need for ether altogether. From that point, the concept of ether, which had lasted thousands of years, was abandoned. However, today, we know that vacuum is not truly empty. In quantum mechanics, vacuum is a ground state that still contains vacuum energy and quantum fluctuations. Virtual particles can appear and disappear in unimaginably short timescales. This is fascinating because it makes Democritus's idea from over 2,000 years ago that the universe consists of atoms and empty space astonishingly close to modern physics. Meanwhile, Aristotle's idea that nature abhors a vacuum, although wrong in the classical sense, is not entirely unreasonable when viewed through the lens of quantum vacuum. Even empty space is not absolutely empty, but filled with energy fields. Conclusion. From Aristotle to Democritus, from Torricelli, Pascal, Boyle, and Guericke to Huygens, Young, Maxwell, Michelson, and Einstein, the history of science has spanned more than 2,000 years debating the concept of vacuum. In the end, rigorous experiments disproved ether and paved the way for relativity and quantum theory. Today, vacuum is no longer seen as absolute emptiness, but as a complex ground state with energy and fluctuations, playing a central role in our understanding of the universe. Science has always advanced by asking seemingly simple questions. What is a vacuum? And that very question, after thousands of years, continues to lead humanity toward deeper truths about the cosmos